All right, welcome back to another installment of physics. And we're looking at energy in systems. So this one specifically is talking about heat transfer and calorimetry. Now this one, of course, is going to be very relatable to sort of everyday real world life. I mean, everything that we've talked about really is, but as you think about how many different times and even in your own body, how much does energy need to transfer into heat, or what we call heat? Okay, what is heat essentially? Well, heat is this process of energy being transferred between two objects, and so heat always flows from a hotter object to a colder object. So you'll understand heat, and you'll say, "Oh, it's hot." And why would you say it's hot? Well, when you walked into a room, what's going to happen is your body is colder than the room, and so then the energy, those little particles that are moving, are actually going to transfer to you, and your particles might be moving not quite as fast, as I've shown with these two arrows right here. And you'll say, "Wow, it's hot," because what you've experienced is heat, the transfer of energy between objects, between particles, and that energy flow from one thing to another always flows from the hotter object to the colder object. We have a couple different ways that this can happen. We talked about last time conduction. So conduction is basically where they physically collide into each other, right? So this is where like say you stuck the pan on top of the stove, the heat from the stove is going to physically hit, or the molecules from the hot stove is going to actually hit the molecules in the pan, heat it up. Conduction. We also have convection. Most of your guys' heating elements or heating apparatuses in your house will use convection, where basically warm air is blasted into a room, and that those warm particles, which are moving faster than the other particles, will eventually spread out into the room and convect. And so convection currents will always happen as the warm air rises, cold air goes down, and then gets warmed up again and rises. And so you kind of have this circular motion, and so it just spreads out. So convection is more of the spreading out of warm air. And typically those initial particles were heated in a furnace by conduction, and then the furnace blew the air around, so convection actually made your whole house warm. And the other one that we have is radiation. You'd experience this as you were out on a hot day with the sun shining down on you, and it comes down and it hits you in your black shirt, right? So and when the black shirt, why does the black shirt get warm? Well, it's because the energy from the radiation from the sun is absorbed by the molecules in your black shirt, and it gets hot. There you are. Whee! And so that would be radiation. So radiation is kind of the idea where it's a transfer of energy by electromagnetic waves. And so these are definitely particle movement, and this is electromagnetic waves, actual movement of energy through the earth, as we would call light. And there's a big gigantic spectrum of it. Your microwave oven uses radiation to heat up your food, as those electromagnetic waves move those water molecules around inside your food. So those are the three kind of major ways of heat transfer. And so the equation that we use to calculate heat is Q. So we call this idea of heat, which is the flow of energy from a hotter object to a colder object, we call it heat. You can also call it heat transfer. Okay, so it's Q. I'm not quite sure why it's symbolized with Q, but it is, so we'll go with it. And so what does Q equal? Well, in any sort of heat transfer situation, you're going to have a mass, and then you're going to be transferring that heat to some kind of material. And so that material is going to have a thing that we call specific heat. So this is specific heat, and in a second we'll look at that a little bit more detailed. So specific heat is basically the amount of joules, right, that it takes to raise the temperature of 1 gram of the substance 1 degree Celsius. Okay, so basically, how much energy do I need to raise a mass a certain amount of temperature? And so everything has a different specific heat. I mean, you'll notice that if you put a a pan on the stove, it heats up real fast. But if you fill that pan with water, it heats up real slowly. So water has a much higher specific heat. It takes a lot more joules to heat up the mass of water than it does the iron pan or the steel pan or whatever it is. And so what else do we need to know? Well, if we know how much energy it takes to raise 1 gram of the substance 1 degree, and we know the mass, then we have that bit, right? And the joules is going to be this right here, because Q is energy, and energy is always measured in joules, times the change in temperature. That's all we need. We also need how many degrees did it increase. So here's a quick little example. In your water heater, let's say that you find that your water heater is broken. Okay, so you replace the water heater and you fill it up, and the water heater takes 75 liters of water. All right, so 75 liters, the nice thing about water is that 1 liter of water equals 75 kilograms. So 1 liter equals 1 kilogram, so that's nice. So we have the mass right there. And let's say that the specific heat, or we know what the specific heat of water is for 1 kilogram of water. So the specific heat of water is 4.184 joules, right? And that's per gram per degree Celsius, right? So degrees Celsius. Sorry about that. Looks like a lollipop there. Degrees Celsius. Don't know why I did that. So per kilogram, all we need to do is multiply this times 1,000. So we have kilograms here, so let's go 4,184 joules, because that's how much energy it's going to take to raise 1 kilogram 1 degree Celsius. And then all we need to know is the temperature. So if we want to know how much heat we're going to have to transfer into this to raise the temperature up to what we want it. Let's say that we start at a bone-chilling 15 degrees Celsius, which is, it's about 58 degrees Fahrenheit, around there. So that's too cold. You're not going to want to jump into that shower. So let's say that that you're going to wait until this sucker heats up to about 43 degrees Celsius, about 110 degrees Fahrenheit. Nice toasty shower. So what's the difference between these two? Well, a change in temperature. So let's just go ahead and say my final temperature minus my initial temperature right there. All right, so if I go ahead and multiply these things out, I'm going to erase this right here. So that's no longer accurate since I filled this in. So my actual amount of heat I'm going to have to transfer to my water heater once I replace it is going to be this. So I have my mass of water, I have the amount of energy it takes to heat up 1 kilogram of that per degree Celsius, and I have my amount of degrees Celsius I need. So this is actually going to give you my total amount of energy that's going to go into that water heater. So if I calculate this out, add these all up, I'll end up with 8.8 times 10 to the 6 joules. Now, one of the other things that comes into play here is because this is energy, right, we have to pay for energy. And so how do we pay for energy? Well, the power company, power, remember, equals energy per amount of time, right? And power is measured in watts. So power is always measured in watts. Now, the power company will charge you per kilowatt hour, right? So how much energy is in a kilowatt hour? So we have to look at, first of all, what is a watt? Well, a watt equals 1 joule of energy per 1 second of time, right? So if we said, well, what does that equal if we're talking about joules? So each joule, right, is going to equal watts times seconds, right? And so what about a kilowatt hour? Well, a kilowatt hour is going to be 1,000 watts, right? Because that's a kilowatt. And an hour is 3,600 seconds, okay? So how many joules is that going to equal? Well, all we're going to have to do is multiply these out. So we're going to end up with, let's just go 3.6 times 10 to the 6 joules. So 3.6 times 10 to the 6 joules is a kilowatt hour. And so in some of your conversions here, you're going to be looking at how does power relate to, as soon as you know the amount of heat that you need to transfer, you can easily convert this into power using this equation right here. Here's your energy. If you know your time, you could find power, or you could do sort of what I'm doing right here. So I want to know how much this is going to cost. I know that my power company charges me I'll put it right here. They charge me 36 cents per kilowatt hour. Okay, so how much is it going to cost me? Well, I need to know how many kilowatt hours it's going to take to heat up this water. So I know that this is how many total joules that it's going to take to heat up, and I know that every single kilowatt hour is 3.6 times 10 to the 6 joules, and that'll never change. So you can sort of have that in your mind if you need to convert to power. And so what is that going to equal? So I divide these things out. It's going to equal 2.4 kilowatt hours, right? And if I multiply that times my $0.36, what do I get? I get 2.4 times 0.36, which is going to be 86 cents. Sweet. So not bad. Not bad at all. All right. Well, so there you go. That's what it's going to cost to do the initial heat up. Now, of course, you got to continually heat that over and over and over again. So you can imagine how this little 86 cents will end up becoming a lot more. But on the side of your water heater, they'll actually tell you how much it'll cost per year. So what they've done is they've just done this equation, factored this in, and factored in sort of a average cost per kilowatt hour, and used the 365 days and sort of an average amount of filling and reheating. And so then they give you that estimate on the little energy saver thing. And so that's where you see that tacked on the side of a water heater, and where you get those efficiency ratings. They're just basically doing this physics right here, knowing that that transfer of energy is going to be happening. All right. And even in this, real quick, we've got these two right here. So if you look at your hot water heater, just kind of add one more little bit. You're going to have elements in here, right? And these heating elements are going to heat the water around them by conduction, right? Because these are going to get super hot. That's where the electricity goes in. So electricity is wired to these two heating elements, and they're going to heat by conduction, and then they're going to flow around inside this water heater like this, and convection is going to cause the whole water of the entire thing to heat up to a certain temperature, and you're going to have a thermostat in here which is going to shut off these things from heating as soon as you get to the right temperature. So there's our conduction and convection. There won't be radiation necessarily in the water heater, but like I said, the microwave oven is going to use it. All right, so hopefully that helps with understanding energy, heat transfer, power, how our energy transfer in our houses and our daily lives transfers into what we see on our power bill, and how you can convert between all of these things and sort of figure out a whole lot of information.